Hello. In this lecture, we are going to see the concept of real matrices. Real matrices means matrices are, before going to see real matrices, first we'll see matrices are broadly classified as two types. One is real matrices, another one is complex matrices. So under real matrices, we'll see three matrices, which is symmetric, skew symmetric, and orthogonal matrices. Symmetric, skew symmetric, and orthogonal matrices. Now we are going to see what is the definition of these three matrices and some properties on these matrices also. Okay. Now, coming to the definition of real matrix. Coming to the definition of real matrix. Let A equals to Aij is said to be real. So here if you look at the notation, A equals to Aij, which stands for, suppose A is a m by n matrix. So it will be like this: A11, A12, and so on, A1n. Similarly, A21, A22, and so on, A2n. So instead of representing like that, right? So simply we will put it in a notation like this: Aij, where I stands here there are two subscripts are there, I and j, where I stands for row and j stands for column. So this is the general notation for representing a matrix. So in this case, let A equals to Aij is said to be a real matrix. When we say that it is real matrix, whenever every element of A is real. So if each and every element of this matrix is real, then we can declare that it is a real matrix. Okay. Now, suppose that A is a real square matrix. So that means each and every element of A is real. Now, this real square matrix is said to be symmetric. When we say that it is symmetric means if A transpose equals to A, that is Aij equals to Aji. That means if you interchange the rows of the matrix A and you are going to get once again the same matrix, then we say that it is symmetric matrix. So that is Aij equals to Aji. For example, if you look at this matrix, A equals to -1, 2, 3, first row, second row is 2, 5, 6, third row is 3, 6, 4. So if you interchange these rows, if you make these rows as columns, see -1, 2, 3, if you make it as column, it is -1, 2, 3. 2, 5, 6, if you make it as column, it is 2, 5, 6. 3, 6, 4, if you make it as column, it is 3, 6, 4. So clearly the rows are interchanged here. So once again you are going to get the same matrix. So whenever it is like this, we say that it is a symmetric matrix. It is said to be a symmetric matrix. So symbolically we'll write this as A transpose equals to A. Next, we'll see skew symmetric matrix. So a matrix, a real square matrix A is said to be skew symmetric if A transpose equals to -A. If A transpose equals to -A. Here also you have to interchange the rows. But here the overall the matrix what you are going to get is minus of the original matrix A. That is Aij is equals to -Aji, or vice versa, Aji equals to -Aij. The example is here this one. B equals to 0, 2, -3, -2, 0, 1, 3, -1, 0. Suppose if you are making the first row as column, then see clearly it is not 0, 2, 3. It is multiplied with minus. So 0, -2, 3. Similarly, -2, 0, 1. If you make it as column, it is coming it as 2, 0, -1 because we are multiplied with -1. Similarly, the third row, we made it as third column by multiplying with minus sign. So whenever it is like this, then we say that it is a skew symmetric matrix. So we say that it is a skew symmetric matrix. So the example is this one. And one interesting point here you have to note down is in a skew symmetric matrix, always the leading diagonal or principal diagonal elements, the leading diagonal or principal diagonal elements. What I am saying is this is 0, 0, 0. The leading diagonal or principal diagonal elements must be always 0. So otherwise you cannot get the skew symmetric matrix. That is true here. See, if you bring this one to this side, Aij plus Aji equals to Aij plus Aji equals to 0. Aij plus Aji equals to 0. So whenever it is diagonal entries, what are the diagonal entries? A11 and A22, A33. That means whenever I equals to j, what happens here? This becomes 2aij equals to 0. From that aij equals to 0. That means it indicating that all the diagonal entries are 0. So that's why in a skew symmetric matrix, always the diagonal entries, the leading diagonal entries are 0. Coming to orthogonal matrix. A matrix A is said to be orthogonal whenever A transpose equals to A inverse, or we can say A transpose into A or A into A transpose equals to I. Example, suppose a matrix C is given like this: cos theta 0, sin theta 0, 1, 0, minus sin theta 0, cos theta. So if you write its transpose, C transpose, and if you multiply with C, definitely you will get the identity matrix I. You will get the identity matrix I. So the advantage is, suppose you want to find the inverse of this matrix and you already know that it is a orthogonal matrix, then no need to calculate adjoint A by det A. Directly, if you write its transpose, that is enough. So you can save time. That is one advantage of the orthogonal matrix. And here a note is there. So what is that note is? Whenever a matrix is orthogonal, always its determinant value, if you calculate its determinant, you will get it is either +1 or -1. This is one important observation. So either you will get +1 or -1. So we see here some important conclusions on symmetric and skew-symmetric matrices, or we can say some properties on symmetric and skew-symmetric as well as orthogonal matrices. So one by one we'll see. So if A is any square matrix, then A plus A transpose is a symmetric matrix, and similarly A minus A transpose is a skew symmetric matrix. So A is any matrix if you take, and if you write it's a transpose, and if you add with the original matrix, that transposed matrix, then definitely that will behave it as a symmetric matrix. The same thing, if you subtract it, it will act as a skew symmetric matrix. And the second one is very, very important property. Every square matrix can be uniquely expressed as the sum of a symmetric matrix and a skew symmetric matrix. So every square matrix can be uniquely expressed as the sum of a symmetric matrix and a skew symmetric matrix. Suppose A and B are two symmetric matrices and you calculated its product AB, then once again it is symmetric. Next, the fourth one is, if A and B are symmetric matrices, then AB minus BA is a skew symmetric matrix. This is one interesting property. A and B are symmetric matrices. If you take its product, it is symmetric. If you take AB minus BA, it is a skew symmetric matrix. Next, suppose a skew symmetric matrix is there and you are calculating all positive integral powers of the symmetric matrix. Suppose A is a symmetric and you calculated A square, you calculated A cube, you calculated A power 4. All the resultant matrices are once again symmetric matrix. This is one property. Next, coming to sixth one. Suppose A is a skew symmetric matrix. So here also you are calculating the powers of that matrix. Suppose you calculated A square, A cube, A power 4. But whereas in the previous case, whenever A is a symmetric matrix, all the integral powers, irrespective whether it is even or odd, you will get symmetric. But whereas in skew symmetric matrix, an important point you have to notice, in a skew symmetric matrix, If it is odd powers, then only you will get it is skew symmetric. Suppose if it is even powers, you will get it as symmetric. That means suppose A is skew symmetric and you are calculating A square, then definitely you will get symmetric. Suppose if you are calculating A cube, you will get skew symmetric. So that is one interesting property on skew symmetric matrices. And coming to orthogonal, suppose A and B are two orthogonal matrices, then the product is also a orthogonal matrix. Like here, symmetric matrices we have seen. Whenever A and B are symmetric, its product is symmetric. In the same style, if whenever A and B are orthogonal matrices, its product is an also orthogonal matrix. Okay. And here also in note we observed whenever it is orthogonal matrix, the determinant of that orthogonal matrix is plus or minus 1. Now we'll see three examples, one for symmetric, another one for skew symmetric, and the last one is for orthogonal. So here, show that the matrix A equals to 1 minus 1 5 minus 1 2 1 5 1 3 is a symmetric matrix. We have to show that it is symmetric. That means calculate its transpose. If you calculate the transpose, what is transpose? Making the rows as columns. So here this row is made it as column 1 minus 1 5. Second row minus 1 2 1, third row. So once again this is the original matrix. Therefore I can declare that A transpose equals to A, therefore it is a symmetric matrix. The next one is show that it is skew symmetric. So first calculate its transpose. So I calculated the transpose here. A is this one, its the transpose is, I made the rows as columns, therefore we got this one. Then I multiplied this entire thing with minus. I multiplied this entire thing with minus. Then this becomes 0 plus 1 minus 1. And here it is minus 1 0 plus 1. And it is 1 minus 1 0. Right. So I can write this matrix as like this. Right. If you send this minus inside, I am going to get the same matrix. Now this I can write it as minus A. So A transpose equals to minus A means clearly it is a skew symmetric matrix. And you can observe clearly here the leading diagonal, that is the principal diagonal entries all are, clearly it is 0. Next, the third example is the matrix is given, right? Now we are checking whether it is a orthogonal matrix or not. So for that purpose, what I have to do? I have write the transpose of the given matrix. I made the rows as columns here. Then I multiplied with the same matrix. Then you will get the identity matrix very clearly. That you can see it here. 3 by 7 into 3 by 7, 9 by 7. 2 by 7 into minus 6 by 7. That is minus 12 by 7. 6 by 7 into 2 by 7. How much it is? 12 by 7. So initially 3 by 7 into 3 by 7, 9 by 7, and 9 plus 12 is 21 minus 12, right? So 2 into 6, 12. So what you are going to get is 7. 7 by 7 is 1, clearly, right? So in that way, we will get this identity matrix. So these are the three examples. Okay, I hope you understood this session. Okay, thank you.